This is the problem. Essentially, in a ship unloading operation, we're unloading a 3,500-pound automobile by a cable, and a worker ties a rope to the cable at A and pulls it in order to center the automobile where he wants it to land. At the moment pictured in the picture, the automobile is not moving, the ring is not moving, and neither is B. Uh, and the angles between the vertical and horizontal are given there as 2 degrees and 30 degrees. So what do we know looking at this problem? Well, we know the weight of the automobile is 3,500 pounds. We'll call that W. Say W equals 3,500 pounds. We know the angle of the cable. Again, the cable is running vertically or near vertical, and it's 2 degrees. So we'll call that angle B because it's at B, and we'll say that's 2 degrees. We'll look at the angle of the rope below horizontal, and that's 30 degrees. So that's what we know from what's given. The main thing when doing a word problem such as this is, what is the question? So we look up here and reread our problem statement, and we see that it's looking for the tension in the rope. And we'll name that, again, T sub AC for tension, and between A and C. And it also says it's the tension in the rope and the cable. So we need to also find the tension in the cable, and we'll call that TAB. Summarize our known information in a table here is a nice thing to do. Now we'll look at this problem, and it's a statics problem. It's not moving. So in statics, the first thing we almost always do is a free body diagram. We try to draw the forces acting on the particle. The particle A has 3 forces acting on it. Again, it's got the tension of the cable up at 2 degrees, and the tension at the rope down at 30 degrees, and the weight acting straight down. We could also include the names over here in our free body diagram. Since we know that information of 2 degrees, 30 degrees, and 3,500 pounds. For the first task, what we'll do is sum of the forces equals 0. And if you remember to some vectors, you can place them tip to tail. That is, you take the starting point of TAC and move it down to the tip of the weight, and then take the starting point of TAB and move it down to the tip of TAC. When we've done that, this is what we end up with. Again, we don't know the length of TAC or TAB at this point. So let's go on and see if we can find that length. I'll be using GeoGebra to work this, and we'll start with this force triangle drawing. So GeoGebra here. First thing I want to do is put a point at 0. I always like to call that O equals 0, comma 0. So I put a point there. And I need to add a point for the weight, because we'll know where the end of the weight is. So I'll add a point at 0. The x value is 0 because it's straight down, and minus 3,500. And GeoGebra automatically gave it a name of A. So that's our weight vector. Now we want our tension in our rope vector. To do that, it wants to be 30 degrees down to the right of A. So I want to put a horizontal line in, and a horizontal line is just y equals minus 3,500 in this case. And then I'll use this rotate tool, and I'll rotate this line. So I'll select the line, and then I'll select the point I want to rotate it about, which is A. And I want to go clockwise 30 degrees. So I hit OK, and I get a new line that's been rotated 30 degrees. I can hide the original line, is OK. Likewise, I want a vertical line, which is just x equals 0. And I want to rotate that line also. So I click the line and the point I want to rotate it about. Now, in this case, I want to rotate it counterclockwise by 2 degrees. Again, above the O is going to the left, so that's counterclockwise. Again, I don't need that original O value. Again, the main point I'm wanting to find is this circle point here where these two lines cross. And to do that, I use the intersect tool. So I'll just intersect these two lines, and that will give me this point where they cross. Now I'll add some vectors. We can hide these lines. We don't really need them anymore. And we'll do a vector from O to A. And we'll rename that one just to be consistent. We'll call that W, because that's our weight vector. And I'm going to move the W over to the other side just to make space later. Now I'll add the vector from A to B. Again, I'll rename that T underbar close AC. The braces make both those the underscore. So we can see TAC, and I'll move it down here where we can see it better. And our final, third vector will go from B back to, let's see, let's start over. Vector from B to O. And that was named U automatically, but we want to rename that again, T underscore A B. So we hit OK and move that out. Now we don't really want the we've got the components of these vectors, but what we really want is the magnitude. And a quick way to get the magnitude in this case is to draw a polygon, because GeoGebra will give me the length of each side of the polygon. So I get A is equal to this TAB. W is equal to B, and TAC is equal to So those my answers. Again, A 3574. The weight is 3,500, which is what we were given. And our force off to the side is 144 pounds. Okay,